Hello students, welcome back to our channel Diksha Karnataka. So as you know, we have started a series where we are discussing on how to complete a chapter. So in today's video, we will be discussing the most important chapter, coordination chemistry from inorganic chemistry. Okay, so I'll be telling you which topics you should put more focus and which type of questions you should practice so that you can complete this chapter effectively in less time. So let us first see the topics in this chapter. So the first topic we have is Werner's theory. Here we'll be discussing about primary and secondary valences. What type of questions are asked, we'll be discussing. Important terms, so you know a lot of definitions in this chapter. So we'll be learning those definitions from where questions are asked. Next is nomenclature, very important topic. Most of the questions will be coming from nomenclature. So I'll be discussing the rules and I'll give you some examples also. Next, isomerism, another important topic. What are the types of isomerism we'll see. And then we have bonding theories. So we have here valence bond theory and crystal field theory. We'll discuss about them. And then we have bonding in metal carbonyls. So this is little less important topic. So we'll just see what are the points to be seen here. Okay, so the first topic is Werner's theory. So according to Werner's theory, we know there are two types of valencies, right? One is your primary valency and another is your secondary valency. Primary valency, what are the properties of primary valencies? They are ionizable and they are satisfied by negative ions, and generally they are your oxidation number, right? Primary valency tells you about the oxidation number. Now secondary valencies are non-ionizable, satisfied by negative or neutral molecules, and they generally tell you about the coordination number. So here you can expect one question like what information does primary valency gives you, right? Some theory based question you can expect from this part. Then secondary valency, you should know that it is non-ionizable. From here you are getting questions like if we add some moles of AgCl, how much precipitate will form, or one compound will be given, how many ions can be formed from that. So that is the part where you can get questions from here. Now going to the next topic, that is important terms. So I'll be discussing some very important terms from where you can expect questions. First of all, you'll get questions from denticity. Okay, what you have to remember, some examples of unidentate ligands, some examples of didentate ligand, and some examples of polydentate ligand. Here EDTA, remember it is a hexadentate ligand. Okay, so just examples you can remember. Ambidentate ligand, what is the definition? That they have two donor atoms but either of the two will donate at the same time. So here also example you can know Sc and NCS can have, you have NO2ONO, right? So these are some examples of ambidentate ligands. So I have not taken all the definitions, coordination sphere and all, because there you will not get questions. Here some important term is there, coordination number. So coordination number you have to just see, for example, the number of ligands a metal atom is bonded to, that is called as the coordination number. For example, here it is 6. Then we have homoleptic and heteroleptic. So homoleptic, what is the example? What is the meaning? That is they should have one kind of donor groups, and here it can have more than one kind of donor groups. So here you can see all the ligands are NH3. So that is why it is a homoleptic, and here you can see there is NH3 also and water also. So it is a heteroleptic complex. Okay, next. The most important topic, that is nomenclature. Okay, very important. One question from nomenclature will surely come. So just let us revise the rules in first go. So first of all, the cation should be named first. Okay, whenever a complex is there, cation part should be named first. Then in the ligands, okay, in the ligands, the ligand should be named in alphabetical order. Okay, you have to follow the alphabetical order. And here also, like for example, there is NH3 group. Okay, two NH3 groups are there. The name is diamine. We have to take diamine, but here the name you have to consider is A. Not, you should not check with D. Okay, so the alphabet you have to consider is the name of the ligand. Okay, next is, this is very important, anionic ligand should end with O. Like for example, if you have chlorine, okay, so chlorine, or so the name for chlorine will be chlorido. Similarly, fluorido, bromido, like that we'll get. So all the ligands which are having negative charge will end with O. And those which are neutral and cationic ligands, there is no change for them. Certain ligands, different name is used for, as aqua is used for water, amine is used for NH3, and carbonyl is used for CO, and then nitrosyl is used for NO. Okay, next, you have to use certain prefixes like mono, di and tri to represent the number of ligands. And if the ligand name is like, if you have this ethane 1,2-diamine, then we should not use di, tri there. We have to use the words like bis, tris, tetrakase to represent 2, 3, 4 in such kind of ligands. Okay. Okay. Next is oxidation state of the metal should be mentioned in parenthesis, and it should be in Roman numbers. Okay. One major, this is very important point. See, if the complex ion is a cation, then the metal ion is named as the same element. For example, iron, then you have to name it as iron. But if the complex ion is an anion, then the name of the metal ends with the letter ATE. Okay, we'll see the examples. I have just explained the rules. Now I'll do some examples here. Okay. So first of all, you see this part is cation, this part is anion, right? This is cation and this is anion. In the cation part, we will name the ligands first. So what are the ligands here? Amine is one ligand. Okay. Next is water. For water, we have to use aqua. And okay, these two ligands are there. So ligand should be named in which order? Alphabetical order. So how many amines group are there? 3. So it will be triamine. How many water groups are there? 3. So triaqua, right? So triamine, triaqua. Both the ligands are done. Now coming to the metal. Metal, you see this metal is a complex of the cationic complex. So there will be no change in the name of the metal. So it will remain as chromium. Then you calculate the oxidation state. You can calculate here, this is my +3, this is 0, this is 0. So I can say chromium in its +3 oxidation state. And then the auxiliary ion, that is your chloride. Here you should remember, auxiliary ions, there should not be like you are mentioning it as trichloride. Okay, auxiliary ions, only name should be there. No di, tri, nothing should come for auxiliary ions. Okay, so this is one example done. Okay, now let us see this one. Here, for such type of ligands, there are 3 such type of ligands. We will not use the word tri. Rather, we have to use tris. Okay, so tris, ethane 1,2-diamine, cobalt, you can check the oxidation state. Here is +3, here it is 2. So that is why we'll get cobalt 3 sulfate ion. Again, you see there are 3 sulfate, but I am not writing trisulfate, right? It has to be mentioned only as sulfate. Okay. So nomenclature is very important. See, I'll recommend you from where minimum 30 examples you have to do. From where will you get this question? Go to NCERT book. Okay, NCERT book, all the in-text questions, all the exercise questions on nomenclature, and you can also practice the examples given. Okay, so different compounds if you do, you will be more you will get more clarity on nomenclature, but minimum 30 examples you have to solve. It's a definite question. Next coming to most important topic, isomerism. So first of all, you have to understand isomerism is of 2 types. First is your optical isomerism and another is your structural isomerism. In optical isomerism, again we have 2 types, geometrical isomerism and stereoisomerism. Whereas in structural isomerism, we have linkage isomerism, ionization isomerism, coordination, and then solvent isomerism. Okay. So we will discuss their examples in detail. First of all, what is geometrical isomerism? It is, you can see, cis and transform. Okay, I have taken 3 examples here. First one is, if you can see, platinum NH3 whole 2 Cl2, right? So here we can have 2 conditions. Platinum can exist with 2 NH3 on one side and 2 Cl on another side. See, you can see both the NH3 are on one side, both chlorines are on one side. So such type of geometry is called as cis geometry. Now if I want, I'll take like this, platinum this side NH3 and another side, opposite side is another NH3, this side chlorine and this side chlorine, right? So if we get this one, 2 NH3s are on opposite side, so this is your trans geometry. Okay, so this example is clear. Now we'll go to little complex example here. Another example is with coordination number 6, CONH3 whole 4 Cl2. Okay, now see, whenever you want to do trans, take these 2 positions as chlorine. Okay, the 2 chlorines are on opposite side and then NH3s are on one side. Okay, so this is a trans geometry. Just you take, now if you want to do cis, that is very easy. Just remove this part and take here chlorine and here NH3, right? So any other configuration apart from where chlorine, two chlorines are on opposite side, apart from that any other configuration you take, then that will be your cis. You can also do, there can be like you do this chlorine here, any other. The only thing is the two chlorine should not be in opposite to each other. So what are the opposite positions? If this chlorine and this position and this position you are considering, or this one and this one, or this one and this one. You should not keep two chlorines in these two position or these two position or these two positions. Apart from that, if you keep any other thing, you will get the cis isomer. Okay. Now this is one example where we have auxiliary ligands, where we have the skeleting ligands. Okay. So again if we have this 2Cl like this, okay, then this is trans form. Okay. And cis form will be what? Just you have to replace this 2 chlorine. Don't keep it in opposite side. So if you do like this, we will get the cis isomer. Okay. So these are geometrical isomers. So now let us go to stereoisomers. So stereoisomers means what? The mirror image should be non-superimposable, right? So one example, first example given to you is COEN whole 3, right? So if you draw this one, I can show you here. See, this is CO and we have this 6 ligands are there connected. If you draw its mirror image, this one, right? So these two mirror images are non-superimposable on each other. So what does that mean? That means these are optical isomers, or we call them stereoisomers. Okay. Now similarly, if we have this one, PtCl2En2. So you can see this image and its mirror image are non-superimposable. Okay. So if these are non-superimposable, they are your stereoisomers. Now what if we take the transform of this one? See here, if the same compound PtCl2En2, its transform I'll take. This is cis form. If I draw the transform, right, this is the transform and the mirror image will be the same like this, right? Now you see these two mirror images will be superimposable on each other. So what we can say, the transform of PtCl2En2 is not a stereoisomer, but the cis form is a stereoisomer, right? Okay, so these were all about optical isomers. Okay, now we will quickly see the structural isomers. Okay, so first is linkage isomerism. For this, the best way to identify a linkage isomerism is the presence of an ambidentate ligands. What are the ambidentate ligands? Generally we have NO2 and SCN. Okay, you will get mostly examples from this one. So you can see NO2 is there. If I write another isomer of this one, where I write like this, right, ONO-Cl2. That means what? Here N is connecting and here O is connecting. That is what ambidentate ligand is present. So it is a linkage isomerism. Then coming to coordinate isomerism. So here what happens? You should have two complexes. Okay, for coordinate isomerism, we need two complexes, and the ligands of one complex can be interchanged with the ligands of another complex. So for example, if I write COCN6 and CrNH36, right? So this, you see what I have done, NH3 I have taken here and CN I brought here. So only the ligands of the complexes are exchanged. Such type of isomers are called as coordinate isomers. Okay. Now let us go to ionization isomers, counter ion. So now you see, whenever you have a complex, this outside one ion will be present. That is called as counter ion or auxiliary ion. Okay. So whenever a counter ion can replace a ligand from the complex, then we call it as ionization isomers. So for example, you see Br is there outside here, NH3 and sulfate is inside. Now what we can do is, what we have exchanged here, Br is taken inside and sulfate is taken outside. You see here, right? So these type of isomers where the counter ions can displace a ligand is called as your ionization isomers. See, you need not read the definitions, but you should be very clear with the examples. Like how questions are asked, they will be giving you certain exam options and which isomerism they show. Okay. or they'll give a compound and they'll ask you what type of isomerisms are possible here. So those type of questions you should solve. So solvent isomerism is very similar to ionization isomer. The only thing is here water has to be present. So when you see water, you can immediately think about solvent isomerism. So here what is happening, see 5 water molecules are there, 1 chlorine molecule is there and 2 chlorine are outside. Now what happens, we can take this water molecule inside and chlorine molecule outside to get this molecule, right? So these type of isomers where water molecule can be exchanged is called as your structural isomerism, solvent isomerism. Okay, now we'll go to bonding theory. So we have 2 important bonding theories. One is your valence bond theory and another is your crystal fill theory. So what is according to valence bond theory? So first of all, according to valence bond theory, the orbitals of metal, right, the valence you can write down, they undergo hybridization to form new hybrid orbitals where the ligands can donate electrons. So this theory part is not required, but you should know these important examples and their shape. So for example, if the coordination number is 4, okay, and the hybridization is sp3, then the geometry will be tetrahedral. If the coordination number is 4 and geometry is dsp2, then hybridization is dsp2, then geometry will be square planar. If you have coordination number 5, hybridization will be sp3d and the geometry will be trigonal bipyramidal. Coordination number 6, okay, it can have 2 types of hybridization, sp3d2 and d2sp3. So we will get geometries like octahedral in both the cases. Okay. So now I have taken some important examples that are there in the NCERT. I have made a table. So first of all, you should remember some important points here. If you have D2sp3, okay, that means this is 3D, this is 4s and this is 4p, right? For 3D series I am telling. That 3D orbital, if it is used, then we will call it as inner orbital complex. Okay. Now, if we have this sp3d2, then it is 4s, 4p and 4d. So when we are using the outer d orbital, we will call it outer orbital complex. So generally, if the ligand is a strong ligand, then we will get this D2sp3 hybridization. If it is a weak field ligand, we will get sp3d2 hybridization. Okay, fine. So you can just remember these examples. NH3 is a strong field ligand, so we will get octahedral and diamagnetic behavior. COF6 will get sp3d2, again octahedral but paramagnetic. NiCl4 is sp3 tetrahedral paramagnetic and NiCN4 is dsp2 square planar and diamagnetic. Okay, so these all the 4 examples are there in NCERT. So you should know their hybridization, geometry and magnetic property. Okay. Fine, now we can go to crystal fill theory. Some theory points are important here. First of all, metal ligand bond is to be assumed to be ionic, right? So this is very important. Metal to ligand bond in crystal fill theory is assumed to be a ionic bond. Okay, statement based questions are asked from this point, so this is an important point. Now what happens, the 5d orbitals are always, they are degenerate. These 5d orbitals are in one energy level until the ligand approaches. So when the ligand approaches, what happens, the d orbital splits, and we have 2 types of splitting in octahedral geometry and in tetrahedral geometry. Okay, now before that we will see something called as ligand field strength. So this is the order, the strongest ligand and this is the weakest ligand. So what will happen, if it is a strong field ligand, the splitting will be more. If it is a weak field ligand, splitting will be less, right? Now we have this formula also, you have to remember, delta T is equal to 4 by 9 of delta O. This is important formula, please remember this. You can get small numericals from here. Okay, fine. So this is clear. What happens here, ligands, all the d orbitals are there. When the ligands approaches, the d orbital split. There are 2 types of splitting. One is your octahedral splitting and another is your tetrahedral splitting. So whether ligand will be strong or weak, it depends on this series. So you can just remember the beginning, some strong field ligands here, NH3, Cn minus, CO, and you can see halogens are weak field ligand. Need not remember the whole series, but some top 4 and the below 4 you should remember. Okay, next. Here is your D block splitting given very nicely. You can see first is this 5 d orbitals, they are degenerate. Then when there is a spherical crystal field, the energy gets uplifted. Then there is splitting. So these values also please remember, 3 by 5 delta O and 2 by 5 delta O. Okay. So this is the splitting in octahedral complex. Okay. Here we will discuss something called as d orbital configuration. Okay. Please all of you see this one clearly. Okay. What I am saying, suppose we have a strong field splitting. Okay. 3 orbitals here and a weak field. If a strong field ligand comes, the splitting will be very high. And if it is a weak field ligand, then the splitting will be like this. Right? Now you see, suppose the configuration is D1. Okay, for D1 configuration, this is my strong field ligand and weak field ligand. Right? So in if D1, then the configuration will be T2G1 for all the cases. This is T2G, this is EG, again this is T2G and this is EG. Now similarly for D2 also it is same, T2G2, and D3 also it is T2G3. Okay. Now coming to D4. Okay, see here, for D4 there are two chances. What happens? Suppose this 3 is filled. Okay, it is a strong field ligand. The 4th electron cannot go to this level because the energy is very high. So what will happen? There will be pairing taking place here. So we'll get T2G4 if it is a strong field ligand. But here what will happen? Since it is a weak field ligand, the electron will move up. So what we will get? T2G3 EG1. Right? So similarly you have to see for D5, D6, D7. Okay. So which configurations are affected by strong field ligand? D4 to D7. Okay. D8, D9, D10 will again be same for both the case. So first 3 and last 3 you have to remove. From D4 to D7, these configurations in strong field and weak field you have to know. Okay. Now this the splitting in your tetrahedral field. So you can see down we have E and up we have T2. So 2 by 5 delta T and 3 by 5 delta T. Okay, fine. Now, this is one important concept, just you have to remember. See, if the splitting is more, okay, if the splitting is very high, then for an electron to jump, so this energy gap is high, energy gap is high. So for an electron to jump from here to here, it will absorb radiation of high energy. Okay, high energy means, can we say that wavelength will be less and frequency will be more, right? So that is what is said here. When splitting is more, why the splitting will be more? Due to the strong field ligands, the light of high energy and shorter wavelength is absorbed and the complementary color is visible. So complementary color we will discuss. Now when next one, when splitting is less, when the splitting will be less, if we have weak field ligand, okay, then that means small energy gap is there. The energy gap is very small. So we need the light of low energy and longer wavelength is absorbed. Okay, so low energy means longer wavelength and the complementary color is visible. So what is this complementary color? See here, if we have like this, okay, if we have, you have to remember this one. See, what does this say? If the compound is absorbing violet color, it will release yellow and the compound will be visible yellow. If a compound absorbs blue, it will be visible orange. If a compound absorbs green, it will be visible red, and vice versa. So that is called as complementary color. Okay. So from here, questions are asked, tricky questions are asked from here. Okay, little tricky questions are asked. You have to practice some more examples for this topic. Okay, now coming to the last topic, not very important topic, but some 3 points if you remember, this topic will be done. So first of all, what is there? A metal carbon bond in metal carbonyl possesses both sigma and pi bond. Okay, this is sigma and pi bond. Okay, so we have here metal and ligand. So metal and between metal and ligand there is both sigma and pi bond. What we have to remember, for sigma bond which orbitals are involved, and for pi bond which orbitals are involved. So you can see MC sigma bond is formed by the, so when the sigma bond will form, when the ligand will donate electron to the metal. Okay, so ligand will donate electron the metal into the vacant orbital of the metal. Okay, so you can see from ligand's filled orbital to metal's vacant orbital. Vacant orbitals of metal and ligand's filled orbital. Okay, that is the donation from ligand to metal to form the sigma bond. Now when pi bond is formed, metal will donate to ligand. This one, metal will donate to ligand. So what is the orbitals involved here? The MC pi bond is formed by the donation of a pair of electrons from a filled d orbital of metal. This is very important. Filled d orbital of metal to the vacant anti-bonding pi star orbital of carbon monoxide. Okay, from the filled d orbital of metal to the anti-bonding empty pi star orbital of carbonyl. So now you can see the diagram here. What is there? Just see here. First of all, from this part, that is your sigma bond, carbonyl is donating to metal. Then metal is donating to carbon from this orbital to this orbital. So this is empty pi star orbital and this is filled d orbitals, right? Okay, so see here. So these are the most important topics in this chapter. So which point or which topics, if I say you have to focus more to get questions, so I'll just list down those topics. First is your nomenclature. Yes, nomenclature is very important. Okay, practice as many questions as you can from nomenclature. Okay, then you have isomers. Okay, nomenclature, isomers. Then we have crystal field theory. So these are the three major topics that you have to practice. Under crystal field theory, what is d orbital splitting, configurations, then color. Okay, these all things will come, right? So yeah, that's all for this video. Prepare accordingly, make a short note of this topic so that you can revise it before your exams. Okay, fine. So thank you. If you have liked this video, if you have found this video informative, so please like it, share it with all your friends who are preparing for KCET, and subscribe our channel so that you can get such videos further. Okay, thank you.